So an extension of the molar volume lab was coming up with an equation called the ideal gas law. And where that came from is this. We now have, through our lab, we now have an entire set of standard conditions. Okay? We always had standard pressure and temperature, those were just kind of agreed upon and given. But now, experimentally, we determined how much volume, how many liters at the standard temperature and pressure would we need if we had 1 mole. So we now have standard numbers for one whole side of this equation. Okay, so each number here, P, V, N, and T, have a set of standard conditions. The idea is, if these are all numbers, we can just calculate them. Rather than sticking 4 individual numbers in there every single time as our standard conditions, let's just come up with the constant number that it always is. Basically, we're going to do the math ahead of time and relate that in all situations. So the idea is we're taking this set of standards, putting in this equation that we've used before, but then knowing that those are our conditions we can relate to all the time. Okay? So P1, we're just taking our standards over here. 1 ATM. Now our lab, we use kilopascals, which is 101.3, but the easier one, more commonly used, is ATM, just because it's 1. Okay? Standard volume is what we came up with in our lab, 22.4 liters. We're going to divide that by our standard amount of something, 1 mole, and we're going to divide that also by our standard temperature, 273 Kelvin. Once I do the math here with the calculator, I simply multiply on the top, divide by what's on the bottom, and I'm going to come up with a number that's 0.082, and then none of the units cancel, so we got this big ugly unit on it, of ATM times liter per mole times Kelvin, and this then is our standard conditions represented as one number because it's easier that way. What we call this number is R, the ideal gas constant. And that ideal gas constant for atmospheres is 0.082. If we had kilopascals, it would be 8.31. That's information that you will be given. You don't need to memorize that. But the idea then is we took this equation, and instead of having to go P1, V1, N1, T1 all the time, we just turn that number, that whole part of it, into something we call R. Then I don't need these little 2's anymore, and get rid of all those. And this is where we rearranged it algebraically and basically multiply both sides by n times t, or n and t here. So if I multiply this side by n and t, multiply this side by n and t, cancels out over here, and just to go on the board, we're going to move it down here. We end up with an equation that is easy to remember as PV equals nRT, the ideal gas law. And that came, again, directly from this number that we developed in our lab. This equation is useful anytime we need to calculate number of moles of a gas, or we're given moles of a gas and we need to calculate volume that it will take up, and things that we can do using BCA tables and stoichiometry.